Hello, we are Group 34. Our project focuses on exposing fake COVID-19 news, and this is our Touchpoint 3 presentation. While social media enables a great amount of communication, it also enables the spread of false information. We have seen over the past 9 months that this is particularly true when it comes to news regarding the COVID-19 pandemic. Our team's ultimate goal with our project has been to create a system that can automatically detect fake news as it pertains to the coronavirus. In this phase of the project, we explored possible classifiers for our dataset via supervised learning. The major components that we set out to accomplish included class balancing, model training and selection, cross-validation, performance metrics, and visualizations.
So, our dataset initially contained about 80% real tweets and 20% fake. However, running a classifier on such an imbalanced dataset would cause the models to classify more tweets as real than fake. To resolve this issue, we decided to oversample the fake data and create a new dataset containing 50% real tweets and 50% fake. We then used the method of stratified sampling to make sure both training and testing datasets contained equal proportions of real to fake tweets. So now moving on to model training and selection, to determine which classifiers worked well for a dataset, we trained multiple classifiers which we believe would perform the best, then compared their performance. We settled on using logistic regression, linear SVM, kernel SVM, random forest, neural net, and finally naive Bayes. The hyperparameters were tweaked for each individual model until reaching their peak F1 score.
The three best performing models were the logistic classifier, neural net, and random forest. On this slide, we can see the performance summary and confusion matrix of each model. The precision and recall of the neural network was slightly higher than the other two. This slide shows a 2D visualization of the classification results. We graph each data point using the normalized first and second PCA components of that point and colorize the point based on the assigned class. The left graph shows the actual true-false labels, and the right graph shows predicted labels. The graphs show an obvious visual similarity, reflecting the high performance of the neural net. In this slide, we graph the correlation between false tweets and words within those tweets. The visualization gives us a feeling for the topics discussed within the misleading tweets. The left graph shows correlations for actual fake tweets, and the right graph shows correlations for tweets we predicted to be fake. We can see that the topics discussed in actual fake tweets are very similar to the topics discussed in tweets we predicted to be fake.
Throughout this touchpoint, we leveraged various types of visualization techniques to get a better understanding of how our models were behaving. Early on, we noticed that due to a much higher number of true labels in our training set, the models could simply output the same result every time and achieve a relatively high accuracy. In order to obtain a meaningful prediction model, we had to resolve our class imbalance so the models would focus on the data features themselves. Additionally, normalizing our PCA dimensionality reduced data frame generated better overall scores for our learning models. Once we had more carefully selected our data and edited our dimensionality, we ran several supervised learning models on this set and found that the neural net implementation yielded the best results.
We hope that this work inspires more research into the detection of COVID-specific fake news and may even inspire social media platforms to implement similar techniques to automatically flag posts for human review. This concludes our presentation, and thank you for watching.